In this video, we'll continue our discussion of higher derivatives by working out another example. So we're given this function. They want us to find the mixed partials. Okay, so I'm going to find my x first. So taking my derivative of x, this first term, notice that the sign only has a y, so that's actually considered a constant. So I get 2x sine squared y. And then we're dealing with x on the other one, so the y squared is a constant. Cosine is negative sine, which is going to cancel out that negative, so I get plus y squared sine x. Not too bad. Let's go ahead and find xy. So now we take the derivative with this y. That sine squared y, let's go off to the side real quick and figure that out. That's the same thing as doing this, and that kind of helps because people will look over this. This is a chain rule. The 2 has to come down. I do sine y to the first, and then times the derivative of sine, which is cosine y. So that's actually what's going to come out of this derivative with respect to y. Now, we do have a 2x, so that's going to give me a 4x sine y cosine y. Right? I don't need to do sine y to the first power. I have that. Okay, and then now this term with respect to y is 2y sine x, thankfully. Okay, so there's that. Now let's do the function with respect to y. Okay, so it's the same idea for that part. So I'm going to get x squared, 2x squared sine y cosine y. That's this term with respect to y. I already did the derivative of that part. And then minus derivative of y squared is 2y, and we keep our cosine x. All right, that's our first derivative with respect to y. Now we have to find our mixed partial. Thankfully, this is all y. So, okay, the derivative of 2x is 4x, and then the trig functions here are in terms of y, so I get to just leave them. And then this last one with terms of x, we have that cosine. The derivative of cosine is negative sine, making this positive 2y sine x. And then I want you to notice this one and this one are the same thing, like we observed in the last problem. So really, we didn't have to do it twice. We could have done it once. I have trust issues when it comes to theorems like that. I don't know why. It's hard for me to believe it. So typically, in my case, when I'm working this out in front of you guys, or if I were on a test, I would do it again. But if you do have trust in theory, which we should, it's been proven, you're more than welcome to go straight from there to there. You don't need to write it down again. Okay, at the end of this, I want to point out a few notes. For any function that is continuous on a region, mixed partials are equal. So again, it was the continuous. If they are continuous, then the mixed partials are equal. Now, here's the deal, is you got to make sure the letters are the same. So what I mean by that is that fxy is the same thing as fyx. That's great. Any combination of y and x would work there. We only have 2. But if I introduce more letters, like g, x, z, y, this is equal to g, x, y, z. But those two things are not equal to g, x, y, x. It's not the same. They have to have the same letters. As long as they have the same letters and they are continuous on the region in question, then you can find the mixed partials and leave them as they stand. Just make sure they have the exact same letters.